Hello, I will now present the advantages of my CVT design on the basis of how system speed is affected by changes in system energy. When analyzing the MM3 system, we can regard it as a collection of different masses of a certain inertia, in this case the flywheel and the programming wheel, whereby the most important concept is that the total energy in the system, measured in joules, is related to the square of the angular velocities involved, where the angular velocity is what we're using to refer to the speed of rotation of the components. Said speed can only be changed when there's a corresponding change to the energy of the system. As for how that is done, that is through the application of power, which is measured in watts or joules per second. Positive power to increase the energy and hence speed can come from user input or a mass, while negative power to decrease it can come from friction or from the loads on the machine, such as lifting marbles. When the machine is in operation, the positive and negative sources of power will be constantly changing in magnitude. Hence, the energy will be changing and also the speed. Thus, the tightness of the system, or the music playing, can be regarded as how little the speed changes for the same change in energy. Let us now look into how this tightness is achieved between these three different systems. In the first case, we simply have a flywheel that is coupled to the rest of the machine by some fixed gear ratio. Each of these will have a mass, and hence a moment of inertia, I. So if we start off with just the system or the programming wheels, it will be rotating fairly slowly, and thus this angular velocity will be fairly low, causing the total energy to be fairly low. So if we didn't have the flywheel, then their energy would be over here, and if we were, say, consuming a total of 75 watts of power, then that energy over time would be depleting fairly quickly relative to what we have, and thus the speed would also be changing fairly quickly. But once we add the flywheel, we also maintain a very large moment of inertia, but we use a gear ratio to make it rotate a lot more quickly, and that thus allows us to go from here to this much total energy, and thus for that same change in energy due to the friction or the fluctuations in input power, we will have a lower overall change in the speed. Then we have the Huygens Drive with Gramophone Governor, which is your current design. So instead of allowing the input power fluctuations to act on the entire machine, we try to insulate the machine from them using this mechanism. So the power input fluctuations will now first go through a small flywheel, then into this Huygens Drive. Now, with how pulleys work, the tension on this chain happens to be equal to half of the force applied by this large mass that is falling. And also, whenever you have changes in the input power, those fluctuations will also show up in this tension, making their way to this output. Thus, the output here comprises both aspects of the input power fluctuations and also of the constant power applied by this falling mass. Now, as far as I understand it, the goal was to make it so that the power applied by this falling mass would be much larger than the fluctuation in power from the input. The problem was that with your current setup, you are trying to keep the mass at a constant height. What that means is that it's not actually moving, and if it's not moving, it cannot do work and thus cannot apply power. Why is that? Because work is equal to force times distance, or power is equal to force times velocity. So if this mass is not moving, then that means that you're actually not achieving your goal whatsoever. But instead, all of the work is actually being done completely by your input power, while some of that work is being absorbed into slightly lifting the mass, or sometimes allowing this mass to fall in order to handle the upstroke of your pedaling. But the point is that this mechanism is not providing as much insulation of your input fluctuations as you think it is. So all this mass is really doing is using its current height to guide the user to supply a constant average power to the machine while not actually doing any work of its own. That is, unlike in a normal clock where we keep this wheel stationary and let the mass fall and do all the work, we instead keep the mass stationary and make the user do all the work. But there are other ways to guide a constant power input, and constant power might not actually be what we want. So that input power makes its way into the Gramophone Governor. What this does is it measures the speed of the drive shaft and uses that to move the brake disc in order to generate a negative power in the form of friction, which it subtracts from the input power. So if there is a constant positive or negative net power changing the energy in the system, the speed, and hence the power subtracted by friction, will increase or decrease until they cancel out and an equilibrium speed is reached. The problem is that if the machine's power consumption changes, then so will the equilibrium speed, and that equilibrium speed can change by a decent amount with not that much of a change in power. To further explain this, our Gramophone Governor comprises these links, these masses, this brake disc and the brake pad. Those are also reflected here. So the links, the mass, brake disc, brake pad. So when the governor is rotating at a certain speed, then this mass here will be flung outward with a certain force proportional to that speed. As a result, that force goes into tension in this link that also pulls this part of that link, and hence the brake disc in this direction with a certain force. So that force then, that is thus producing a friction, is proportional to this rotational speed. And if you zoom out here, you can do the whole geometric analysis, and from that you can solve that friction force is proportional to the square of the drive shaft speed with which this governor is rotating. So this I've plotted over here as a quadratic function. Now it doesn't start at this part of the quadratic because the system has already accelerated such that this disk would meet this brake pad at a certain point rather than at the very start. So given that, this increases increasingly. So if the brake disc is pushing on the brake pad from a particular radius with a certain amount of force, then you will in turn get a certain amount of friction force, which will create a torque acting on your system. So if that torque is applied while the system is rotating at a certain angular velocity, when you multiply the torque by that velocity, you end up with the power that is being dissipated by the gramophone governor. So if the gramophone governor is currently dissipating this much power, then if the system comes to increase to, say, have this much power that it is currently taking in, then the gramophone governor will speed up with the system until it starts to dissipate that same amount of power, canceling out that net power, thus leading there to be no more changes in the speed. So that means that for each net power intake and outtake of the system, there will be an equilibrium speed for which that is completely cancelled out by the power dissipated by the gramophone governor. Thus, in order for the system to be tight, it must require a very large change in the power for a given change in the speed. And in order to increase that steepness, you must either increase the spring force, so if you decrease it, that will reduce the steepness, or you must increase the mass, though that only helps so much, as you can see, or you must increase the size. So to maintain the tightness of the machine, you must either minimize the fluctuation of its power consumption, or you must increase the size of the flywheel so as to average out the changes in speed resulting from those fluctuations, or you must operate the gramophone brake with much higher friction so as to require a much greater change in power for the same change in equilibrium speed. As for why this design appears to work, it is because of the lack of a changing load and the efficacy of the visual feedback provided by the Huygens weight, not due to the design's resilience against changes in system energy. It would have probably worked just as well for a constant load if you were to have bypassed the Huygens Drive, removed the gramophone brake, and just adapted your input to keep the governor's sleeve at the same position. We thus arrive upon my derivative well CVT controller design, which can handle almost any fluctuation in the input power and the system's load. This design places a wheel and disc CVT or equivalent between the input and the flywheel and uses a centrifugal tachometer to measure the speed of the drive shaft in order to control the horizontal position of this control wheel to set the gear ratio from 0 to infinity. Thus, if there is an energy surplus in the system, the tachometer will detect the resulting acceleration and increase the gear ratio to absorb that energy into the flywheel. Likewise, if there is an energy deficit, the tachometer will detect the corresponding deceleration and decrease the gear ratio in order to put that energy from that flywheel back into the system to maintain the speed. Given that, due to the way the CVT is set up, it is virtually impossible to exceed the target speed by a certain percentage because the flywheel would be able to absorb that energy almost indefinitely. Likewise, it would require a dissipation of the entire energy of this flywheel in order to decrease the speed by the same percentage below the target. I will now present these concepts visually using graphs. So firstly, this horizontal scale is measured in RPM, but due to limitations of Desmos graphing calculator, I have made it so that 0.6 equals 60 RPM. Likewise, for the vertical scale, this is measured in kilojoules, so this here, 0.8, is 800 joules. In this model, I am assuming programming wheels of a combined width of 3 meters, a diameter of 1 meter, and a thickness of 3 centimeters. Then for the flywheel, I'm assuming that it is annular in shape, has a diameter of 2.5 meters, and happens to be mainly constructed of foam so as to only weigh about 25.5 kilograms. The purple graph plots the total energy in the system with respect to the speed of the drive shaft for the case where the flywheel has a 1-to-1 fixed ratio with the drive shaft, and the drive shaft has a 60-to-1 ratio with the programming wheels. This total energy is calculated using the previously shown equation of 1/2 I omega squared, where I is the moment of inertia of the programming wheel and the flywheel in this case being made to have 10 times the moment of inertia of the programming wheels, and the angular velocities here are such that the programming wheel is spinning 60 times slower than the flywheel. This dashed green line shows a target speed of 60 RPM for the drive shaft, while this dashed red line shows the total system energy at that target speed, in this case 787 joules. So if the machine accumulates an excess of around 100 joules, then that would increase the speed from 60 RPM to around 64 RPM. Likewise, if it were to lose 100 joules, then that would decrease it to around 55 RPM. The green curve shows the exact same plot of energy versus driveshaft speed, but for the exact same flywheel being connected to the driveshaft using a CVT. So imagine taking this governor design and using the position of this sleeve to measure the current speed of the driveshaft. Then imagine that we used the position of this sleeve to set the position of the control wheel here to set the gear ratio between these upper and lower CVT discs. That connection implies that if the driveshaft speed decreases by a certain percentage, then this control wheel will move such that the gear ratio would decrease towards 0. Likewise, if the driveshaft speed increases by that same percentage, then the control wheel will move toward a gear ratio of infinity. Those lower and upper percentage bounds on the driveshaft speed are represented by these two vertical solid green lines. So as we decrease the driveshaft speed toward the lower bound, the gear ratio between the flywheel and the driveshaft likewise decreases towards 0, decreasing the flywheel speed and hence steeply decreasing the system's total energy. Likewise, as we increase the driveshaft speed toward the upper bound, the gear ratio increases toward infinity. That causes the flywheel to go ever faster and faster, causing our energy requirements to increase, and as such, we will never ever meet that upper bound on the speed so long as the CVT does not slip. So if we take our definition of tightness as being a smaller change in system speed for the same change in energy, then clearly this design with a CVT is substantially tighter than the plain flywheel design where the flywheel is of the exact same mass. And if you thought that that performance was impressive, notice that I've set these bounds to be 50% of the total 120 BPM tachometer range of this simulation. So what happens if I change that to be 1%? As you can see, that energy curve just gets steeper and steeper until it's basically a vertical line, almost. So if I were to sample a certain part of that curve, then for the same changes in energy, we have an absolutely minimal change in the speed. But to achieve this incredible performance, we need to be able to change the gear ratio by a much greater amount for the same change in speed. So let's say that for the CVT discs, we have a range of 15 centimeters to get from a gear ratio of 0 to infinity. Likewise, let's say that for our tachometer, we have to move 50 centimeters to get from an indication of 0 RPM to 120 RPM. So to achieve that 1% tolerance bound, we'd have to take 1% of the 50 centimeter motion range, in this case 5 millimeters, and multiply that upwards into 15 centimeters of motion. So that would be a 30 times gain. That much motion amplification would require a lot of force, which can be supplied by the torque amplifiers that I described in my original video. One thing to note is that there are actually other ways to arrange this CVT. So instead of having two discs sandwiching our control wheel, we can have just a lower CVT disc, and then the control wheel is driving the flywheel, or we can have it the other way around. So in this case, basically we're only controlling the lower bound using this pole, while here we're only controlling the upper bound on the speed. So this I've represented with that red graph that you would have seen. So as we increase in speed, then flywheel can accelerate indefinitely, and we'll never exceed this upper bound, but we're allowing it to exceed the lower bound here, even while the flywheel is still spinning, like so. And with that arrangement, you can see that it still performs a lot better than the plain fixed ratio flywheel, but it's not as good as the bidirectional system with 2 discs. Now what if we want to see how the driveshaft speed varies as we vary the energy in the system with respect to time? So in this case, for these kinds of functions, you can just calculate what's called the inverse, but for this big complicated function, let's say that Wolfram alpha did not like it, so I had to come up with a nice approximation that is good enough, and with that, I was able to come up with these plots. So now we can see how the values change with respect to time. So first we have the total energy in the system, which starts off at 787 joules, and is changing due to a pedaling input. So here I'm assuming that that pedaling input is trying to achieve an average of 75 watts of power, and here we're having 2 strokes, one for each leg, per second. And finally, we have the output here, which is the driveshaft speed as a result of that energy fluctuation. So this is when we have a flywheel with just a fixed gear ratio, so not very good. But now here we have a CVT involved, and that's assuming a rather generous 50% tolerance range, and we're doing quite well. And of course, I can make that better by increasing the control gain all the way down to 1%, and so on. And likewise, what happens then is if I increase the power to something crazy, then we can see that as the time progresses, the energy almost gets completely depleted. So our flywheel here is having a hard time resisting those changes in energy, but as you can see here, so long as we maintain a very high control gain, it is still possible to maintain that 1% tolerance. So it only struggles in giving energy back to the system because that's finite, whereas it can absorb an indefinite amount of energy. So if I increase that tolerance range again, then you can see that a bit better. A lot easier at absorbing, struggle a bit when giving it back. Then I can simulate what happens if we have an absence of input and just a constant dissipation of power, like so. So now you can see that it will take 10 seconds, or 10.5, for the flywheel case to come to a complete stop, whereas with my design, all of that energy of the flywheel is able to be put back into the programming wheels to keep them within the lower bound. So it would take 10 seconds not to come to a complete stop, but rather to come to the lower bound, like so. So you can see here, we zoom in, slowing down very slowly, just to this point. And then, yeah, technically the stuff to the right of here is not valid for the simulation. Alright, I hope this presentation has made it much clearer why this new design is so much better at keeping timing than this original design. Thus, what we need to do is to determine what the expected energy fluctuations of the actual marble machine will be, and from that determine whether or not something with this kind of performance is actually necessary.